Welcome back to educator.com. This is linear algebra, and today we're going to be talking about finding the inverse of a matrix. The inverse is kind of analogous to a reciprocal as far as the real numbers are concerned, but again, like matrices with respect to real numbers, a lot of the things carry over, as you remember from some of the properties like commutativity of addition, distribution, things like that, but certain properties don't carry over. So we can certainly think about it, analogously if we want to, but we definitely want to understand that matrices and real numbers are very different mathematical objects, even though they do have certain things in common. Okay, let's go ahead and get started. So finding the inverse of a matrix, let's start off with a definition. So an n by n matrix, A is called non-singular or invertible if there exists, and remember this reverse E, it means there exists, an n by n matrix B such that A times B equals B times A equals the n by n identity matrix, which remember the identity matrix is that n by n matrix where everything on the main diagonal is a 1. So the analogy as far as real numbers is concerned is kind of like taking the number 2 and multiplying it by 1/2, you get 1, or 1/2 times 2, you get 1 because the 2's cancel. Well, 2 and 1/2 are in some sense inverses of each other, so when you multiply them, you get the identity for the numbers, the real numbers, which is 1. Well, the analogous identity for matrices is the 1 and along the main diagonal. So this is the definition. An n by n matrix A is called non-singular or invertible if there exists an n by n matrix B such that this holds. A times B equals B times A gives you the identity matrix. Okay, so B is called the inverse. A. Oh, real quickly, both of these terms are used interchangeably. Sometimes I'm going to use non-singular, sometimes I'm going to use invertible. To be perfectly honest with you, to this day, for me, non-singular, it always takes me a couple of seconds to remember what that actually means. So when we say non-singular, we mean that it's invertible. That means an inverse actually exists. We're going to run across in a minute matrices that are singular, which means that they're non-invertible, which means that an inverse doesn't exist. So again, you're welcome to use each one. We'll be using both interchangeably, and eventually I think you'll just be comfortable with either one. Okay. And as we just said, if no such matrix exists, then A is singular or non-invertible. I think some of the confusion comes from the fact that sometimes we use non-singular and invertible and singular non-invertible. Okay, so let's just take an example. A nice little 2 by 2. We have 2, 3, 2, 2. This matrix right here. And again, use mathematical software. It gives you the inverse just like this. So B happens to be -1, 3/2, 1, -1. So there are two matrices, A and B. Well, when we actually multiply A times B, and when we multiply B times A, and remember, matrix multiplication does not commute, so they're not necessarily equal, but in this case, AB does equal BA, and they both happen to equal the identity matrix, which is equivalent to this thing, 0, 1. Again, a matrix with 1s along the main diagonal. Okay. If a matrix has an inverse, the inverse is unique. Again, you can't have 2 or 3 or 4 different inverses. You only have one. We won't prove this, but it is actually it's a rather quick proof, but we won't worry about that. We're concerned with using this idea as opposed to proving it. Okay, let's talk a little bit about notation. We want to denote the inverse of A as A with a little -1 as a superscript, and B, which means nota bene, which means, notice this very carefully. This is symbolic, okay? What that means, this A to the -1, it's a symbol. This A to the -1 does not mean 1 over A. This doesn't work for matrices. It's not defined. This is strictly a symbol that we use. Sure, you're used to seeing numbers like 2 to the -1, which is equivalent to 1/2. You just flip it. That's not the same here. We use the same symbolism, but it is only symbolic. It doesn't mean take 1 and divide by a matrix. Division by a matrix is not defined. It's not even something that we can deal with. But so bear that in mind. Excuse me. Now let's list a couple of the properties of non-singular matrices. And again, non-singular means invertible, ones that actually have an inverse. And recall again, we're talking about square matrices, n by n, 2 by 2, 3 by 3, 4 by 4, and so on. We don't speak of inverses of other matrices. Okay, property A. If I have the inverse, and if I take the inverse of the inverse, I recover A, which makes sense. You take the inverse again, you're back where you started, which is actually the definition of inverse. It works in a circle. If you remember dealing with inverse functions, it works the same way. B, if I take 2 matrices, A and B, and multiply them, and then take the inverse, I can actually get the same thing if I take the inverse of B first, multiply by the inverse of A. And notice the order here. This is very, very important. Just like with a transpose. When we did A times B transpose, that's equal to B transpose times A transpose. This same thing here. Those of you that are actually working from a book are interested in actually seeing the proof of this, I would encourage you to take a look at it. Again, the proof is not complicated, it's just a little tedious in the sense that you're dealing with every individual little detail. So it's easy to follow, it's just arithmetic. But it's sort of interesting to see how something which is not very intuitive would actually end up looking like this. So make sure that the order is correct. We also have a B prime, which is just the same thing for multiple entries. So if I have, for example, A times B times C times D, so on, inverse, well, I just reverse them. I'll just do it backwards. That's equal to D inverse times C inverse, B inverse, A inverse. Just work your way backwards, just like the transpose. And C, our final property, if we take a matrix and take the transpose of it, and then take the inverse of it, well, what we can do is just take the inverse first, and then take the transpose. In other words, the transpose and the inverse are switchable. Okay. Let's see what we can do. We want to find a practical procedure for finding the inverse of any given matrix. And here it is. It's actually very, very simple. It's something that we've already done. We're going to be using Gauss-Jordan elimination again. We're going to be doing reduced row echelon form, except now we're going to put 2 matrices next to each other. We're going to be doing it simultaneously, and then the one on the right that we end up getting will actually be our inverse. It's really quite beautiful. Step 1, form. And don't worry if this procedure, as I write it out, doesn't really make much sense. Once you see the example, it'll be perfectly clear. Form the n by 2n matrix. augmented by the identity matrix. Step 2. Transform the augmented matrix to reduced row echelon form, this entire matrix here. Transform the entire thing to reduced row echelon, again using mathematical software. I can't tell you how wonderful mathematical software is. It has made life so wonderful. It's amazing. Final 3. Now, we have a couple of possibilities. Suppose, after converting it to reduced row echelon form, you've produced the following matrix, C, D. So basically, after conversion, A has been converted to C. This identity matrix has been converted to D. Here are the possibilities. If C turns out to be the identity matrix itself, then D is your inverse. So really all we've done, we've taken the original matrix, put the identity matrix next to it, and then we've reduced it to, we've done a reduced row echelon form. Well, it converts, if the inverse actually exists, A, this thing becomes the identity matrix, and the identity matrix becomes the inverse. And B, if C doesn't equal the identity matrix, then C has a row of zeros, and this implies that A inverse does not exist. Okay, so we form the n by 2n matrix. We take the matrix, put the identity matrix next to it. We transform it to reduced row echelon form. If this happens to be the identity matrix, then our matrix D is our inverse. We're done. If it's not the identity matrix, one of the rows will actually be all zeros. That means the inverse doesn't exist. Let's do some examples. Okay. We want to find the inverse of A. So let's do A equals 1, 1, 1, 0, 2, 3, 5, 5, 1. Okay, so step 1, we want to go ahead and form the augmented matrix. So we take the, let me just do a little line here. So we go 1, 1, 1, 0, 2, 3, 5, 5, 5. And we're going to augment it with the 3 by 3 identity matrix. 0, 0, 1, which is just ones along the main diagonal. Let me go ahead and put brackets around this. Okay. And then we convert this to reduced row echelon form. Let me go down here. So we run our math software, and what we end up with is, and again, reduced row echelon is unique. You'll get 1, 0, 0, 0, 1, 0, 0, 0, 1. And over here you'll get some fractions. 13/8, minus 1/2, minus 1/8, minus 15/8, 1/2, 3/8, 5/4, you get a 0, and you get minus 1/4. So sure enough, now we ask ourselves, is this the identity matrix? It is. 1 along the main diagonals, everything else is 0. It is 3 by 3, so the inverse exists. And not only does the inverse exist, there's your inverse. So we've done the existence, and the process itself gives us our inverse. So A inverse equals, well, I'm not going to write it out, but again, that's your matrix. 13/8 minus 1/2 minus 1/8 minus 15/8, 1/2, 3/8, 5/4, 0, and minus 1/4. That means that A, the original matrix, times this gives me the identity matrix, and this times that gives me the identity matrix. These are inverses of each other. Okay. Let's do another example. This time we'll take A equal to 1, 2, negative 3, 1, negative 2, 1, 5, negative 2, negative 3. Okay, I'm just going to go ahead and augment it already to the right. Again, this is 3 by 3, so we have 1, 0, 0, 0, 1, 0, 0, 0, 1. We will subject it to reduced row echelon. When we do that, what we get is the following matrix. 1, 2, negative 3, 0, negative 4, 4, 0, 0, 0. And we get 1, 0, 0, negative 1, 1, 0, negative 2, negative 3, 0. This is not I3. That is not the identity matrix. Therefore, A inverse does not exist. This is actually kind of amazing to think that you can just sort of pick a collection of numbers and arrange them in a square. Sometimes an inverse exists for it, and sometimes it doesn't, by virtue of the actual identity of the numbers. Just as an aside, there's some really, really strange and beautiful mathematics going on here. So every once in a while, it's nice to sort of pull back away from the computation, away from the practicality of what you're doing, and think about some, this is elucidating some very, very deep fundamental truths about nature and how nature operates, and about the things which exist and the things which don't. So that's what ultimately makes mathematics beautiful, in addition to, of course, its practical value. Okay. So let's talk about linear systems and inverses. So we dealt with matrices, inverses. Now let's associate it with linear systems, because again, ultimately, we're going to deal with linear systems. Okay, so let's write a few things down here. If A is n by n, then Ax equals B is a system of n equations in n unknowns. So let's take just an example of n equals 3 as opposed to doing it in its most general case. So we have, so you remember this is the matrix and vector representation of the linear system. We can take a matrix, multiply by the vector x, the vector of variables, which is just in this particular case, maybe a 3 by 1, and it's equal to a 3 by 1 vector, and a vector is just that thing with a, it's just a 1 by m matrix, in other words. So we have something that actually looks like this. A11, A12, A13, A21, A22, A23, A31, A32, A33, and of course these are just the entries. The first number is the row, second number is the column, just as a quick review, times x1, x2, x3, your variable vector, equals b1, b2, b3. So this is a symbolic representation, shorthand notation, if you will, of the entire system. That's what it actually looks like when you spread it out. This is our quick way of talking about it. Now let's do something with this to see what happens. Let's rewrite it again. We have, let's write it over here. Ax equals b. Okay. Now, we just talked about inverses. So presuming that A actually has an inverse, well, an inverse is just another n by n matrix, so we can multiply by A. So let's go ahead and multiply by A inverse on the left-hand side. And of course, in an equality, anything that I do to the left-hand side, I have to do to the right-hand side to retain the equality. So let's multiply both sides by the inverse. So I end up with something like this. A inverse times Ax equals, well, A inverse times B. Well, properties of matrices. This times that, associative. So why don't I just associate these two? So I can write this as A inverse times A, put those together, times X, equals A inverse times B. Well, A inverse times A, it's just the identity matrix. So it's identity matrix X equals A inverse times B. And the identity matrix times something, it just is the identity matrix. It gives you that thing back. So identity matrix times X just gives you X equals A inverse times B. Stop and take a look at that one for a second. Okay. So if A is non-singular, we've discovered a way of actually finding the unique solution for the variables. It's equal to, well, if I take this and if I just multiply on the left by the inverse of the original matrix, the coefficient matrix, I actually find my solution. X equals the A inverse times the B. So just by using the inverse in standard mathematical manipulation that we're all familiar with, we've actually come up with a way of finding a unique solution for this. So let's actually list this as a theorem. Linear systems and inverses. So if A is n by n, actually the theorem that I'm going to list is for homogeneous systems, and in a little bit we'll actually talk about non-homogeneous systems where the right-hand side actually does have a vector b, not just all zeros. Then the homogeneous system, x equals 0, and remember this is the zero matrix, it's all zeros. The zero vector, I mean, all the entries are zeros, has a non-trivial solution if and only if A is singular. And remember, singular means non-invertible. So for a homogeneous system, notice what we just did before for the AX equals B. We noticed that if we have a system AX equals B, if A is non-singular, meaning if it is invertible, if the inverse exists, we can use the inverse to actually find the solution X by just multiplying B on the left-hand side, to the left of B, by that inverse matrix. For the homogeneous system, it's actually different. For the homogeneous system, when the solution set is all zeros, then it has a non-trivial solution if and only if A is singular. In other words, for the homogeneous system, if the inverse doesn't exist, then I can conclude that the system has a solution. This if and only if, you'll actually see it a lot in mathematics, and all this means is that you'll see it symbolized like this as a little aside. It just means it's equivalent to. What this actually says is that that this solution has a non-trivial solution means that A is non-singular, or it means that if A is singular, or if A is singular, then it has a non-trivial solution. So in other words, it goes both ways. Let's do an example. Let me draw a little line here. Okay. Let's consider the linear system. Do it in matrix form. 1, 2, -3, 0. And we'll do the augment here to show that we're talking specifically about a homogeneous system. 2, 0, 5, -2, -3, 0. Okay, so this says x plus 2y minus 3z equals 0, 1 minus x minus 2y plus 3z equals 0, 5x minus 2y minus 3z equals 0. Okay, let's see if we can find the inverse. When we form the augmented matrix, we have, let's do 1, 2, -3, 1, 0, 0, 1, -2, 1, 5, -2, -3, 0, 1, 0, 0, 0, 1. and then we subject it to reduced row echelon form. Let me move it over here, and what we end up with is the following: 1, 0, -1, 0, 1, -1, 0, 0, 0. We don't even have to worry about the other entries. It actually is not relevant, simply because we notice here we don't have the identity matrix. Therefore, we don't have the identity matrix. That means that A inverse does not exist, which means that it is singular. And according to our theorem, if it's singular, that means that this solution, this system does have a solution. So again, singular, non-invertible. Singular, it's non-invertible. That means that this has a solution, okay? Different than the other way. So this is very, very unusual when all of this, when everything on the right-hand side is equal to a 0, the matrix has to be non-invertible for there to be a solution. Whereas if there are a series of numbers here on the side, we need it to be non-singular. We need to be able to find an inverse in order to be able to find a solution for it. Okay. Okay. Let's see. Let us forward. Okay. So now let's talk about some theorems and something which is something called a list of non-singular equivalences. This list is going to be very, very important for us throughout the rest of linear algebra. We're going to be adding to the list, and it's actually going to get quite long. And again, this list of non-singular equivalences allows us to move back and forth between things that are equivalent. When I know something about a system, I look through this list, I can tell you something else about that system. Let's start with a theorem first, though. So we have, if A is an n by n matrix, then A is non-singular or invertible if and only if the linear system AX equals B has a unique solution. That was that thing that we did when we multiplied on the left by the inverse. So this if and only if, again, it just means that it goes in both directions. If A is non-singular, that means that the system AX equals B has a unique solution. The other way, it means if AX equals B has a unique solution, that means that A is non-singular. Now you might think that it's overkill to actually state it as an equivalence, to actually explicitly say that it has to work forward as well as backward. As it turns out, if you remember from your geometry course where you studied logic, where you did if P then Q, it doesn't always work the other way around. So for example, if I said, if it's raining today, then it's cloudy, that's true. But if I reversed it, and if I said, if it's cloudy, then it's raining today, that isn't necessarily true. We can have a cloudy day, but without it raining. So it's very, very important, especially in mathematics, to make sure that things go both ways, or if not both ways, we have to specify that it's only one way. That's why we list things the way we do. That's why we write things the way that we do. Math is very, very precise. Okay, so the list of non-singular equivalences. Now, this is not like, these are equivalences, which means that 1 is the same as 2, is the same as 3, is the same as 4. What that means is any one of these can replace any other one of these. This doesn't mean that if this is so, then this is so. They're all equivalent. They're just different ways of representing the same thing. If I know that A is non-singular, I also know that AX equals 0, the homogeneous system, has only the trivial solution. Because our theorem said that if it's singular, meaning non-invertible, then it has a trivial solution. But here we're saying that A is non-singular, it's invertible. That means the homogeneous system only has the trivial solution, meaning all of the x's are equal to 0. That A is row equivalent to the identity matrix, which is what we did before. We set up the augmented matrix, we converted one to the other, the normal matrix became the identity, and the identity became the inverse. And the system AX equals B has a unique solution. So these are the first 4 equivalences, and each section that we actually move forward to, we're going to add to these equivalences, and by the end of the course, you'll have a whole series of equivalences for non-singularity. or invertibility. So obviously invertibility, non-singularity is a profoundly important concept in linear algebra, absolutely central. Okay, let's see what we can do here. Let's do an example. Okay, we want to know, let's go back to black. Does the following system have a non-trivial solution? Okay, our system is 2x minus y plus 5z equals 0, 3x plus 2y minus 3z equals 0, x minus y plus 4z equals 0. Okay, so non-trivial solution means singular matrix. In other words, the matrix formed by 2, negative 1, 5, 3, 2, negative 3, 1, negative 1, 4 should be singular. Well, let's check. We go ahead and we form the augmented matrix. So we'll take 2, negative 1, 5. We'll do 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we'll finish this one off. 3, 2, negative 3, 1, negative 1, and 4. We will subject this to our mathematical software, and we end up with the following: 1, 0, 1, 0, 1, negative 3, 0, 0, 0. Okay? Doesn't matter what these are. There are entries, of course, but they don't matter because we notice this row of zeros. So we're definitely talking about something which doesn't have an inverse, which means that it is singular, which implies that, yes, there exists a non-trivial solution. Those of you that go on into work in the sciences, particularly in engineering, oftentimes it's true that you're going to be interested in finding the solution to the particular equations that you're dealing with. But as it turns out, a lot of times you're going to be looking for the quality of the solution. Sometimes the quality of the solution, meaning not necessarily the solution, but what you can say about it. As much as you can say about it without actually finding it, will, believe it or not, give you more information than the actual solution itself. Sometimes it's possible to find the solution to a problem, sometimes it isn't, but you can infer different properties of the solution without actually finding the solution itself. And again, oftentimes the qualitative value of the solution is going to be more important than the solution itself. And of course, a lot of this will make sense as you go on in your engineering studies. But just to let you know, sometimes it's nice to know whether something exists or not before we actually decide to find it. In fact, the history of mathematics is replete with hundreds of years going by with people looking for a solution to a particular problem, only to discover several hundred years later that the solution doesn't actually exist. So they were looking for something that didn't exist. Very curious. Okay, so now let's go ahead and solve this. So let me see what we have here. Okay. So let's go ahead, when we decide to actually find the solution itself, we will do row reduction on the augmented matrix. So we do 2, negative 1, 5, and we just take the matrix and the absolute linear system and subject that to reduced row echelon. 3, 2, negative 3, 1, minus 1, 4. Okay. Reduced row echelon form, we get the following. We get 1, 0, 1, 0, 0, 1, negative 3, 0, You get 0, 0, 0, 0. Again, when we're reducing just the system itself to reduced row echelon, this row of zeros is not a problem. Here we have a leading entry, here we have a leading entry, here we have a parameter. So we can just read this off. If we say that this is x, this is y, this is z, what we end up with is x plus z equals 0. And we get y minus 3z equals 0. So z is our free parameter. This is the implicit solution. We can leave it like that. Or we can say z is equal to s. We can say, then put z back in here, we can say y is equal to 3s. And we could put x is equal to negative s. This is the explicit solution. S, you just put in any value you want, solve for x, y, and z. So in this case, not only a non-trivial solution, an infinite number of non-trivial solutions. Okay. Let's do a slightly more complex example. Find all values of a such that the inverse of a, which we'll take as 1, 1, 0, 1, 0, 0, 1, 2, a, exists. So find all values of a, that's a right here, such that the inverse of this thing actually exists, meaning it is non-singular, it is invertible. So we'll say inverse exists. That implies that it's non-singular. And going back to our list of non-singular equivalences, that means that it's row equivalent to, in this case, this is a 3 by 3, row equivalent to I3. In other words, I should be able to, by a series of those things that we do to convert it to a reduced row echelon form, I should be able to convert this to the identity matrix, the 3 by 3 identity matrix, where 1's all along the main diagonal. So let's go ahead and actually do that and see what happens by using A. And here's where mathematical software absolutely comes in. It'll do this entirely symbolically for you. And here's what we get. We get 1, 1, 0, 1, 0, 0, 1, 2, A, 1, 0, 0, 0, 1, 0, 0, 0, 1. That's our augmented matrix. What we want to convert it to, when we do reduced row echelon form, it ends up being the following: 1, 0, 0, 0, 1, 0, 0, 0, 1. You end up with 0, 1, 0 here, 1, minus 1, 0, and you get minus 2 over A, 1 over A, and 1 over A. This process gives us the inverse. This is A inverse right here. We've done it, converted it. It's row equivalent to, this is row equivalent to I3. In the process of doing that, we've actually created the inverse right here, and the only thing we have to look out now is, what does A have to be to make this defined? Well, as it turns out, A can be absolutely anything, but A cannot be 0. So A not equal to 0, it's kind of curious to think you have this system. Any number here will work, but the minute you put a 0 here, you've all of a sudden created a matrix where the inverse doesn't exist. So we've used the same process, except here we have a variable, math software, reduced row echelon form. We've come down, we've created this, We take a look here to see what is it that makes this defined. Well, as long as a is not 0, these numbers are perfectly well defined. Okay, so that was dealing with inverses. Thank you for joining us here at educator.com. We'll see you next time for linear algebra.